Okay, I've selected the next tab, the Steam Power Plant Design tab, which is going to be one of my I guess I'm in a group by myself, one of my designs here. So I've made a little starting place, 10 MPa 500 degrees C for state 1, and I've put some values in here. Let's just take a quick look at that. So the equation is a function that's actually a macro that I wrote when I was in graduate school that is water, and then pass it some parameters. The first parameter is what's given, so temperature and pressure. The next parameter, has to be in quotes, is what property do I want, the enthalpy, and then where those values are located. So in this case, the first one is E10, that's the temperature, and the second one is E11, the pressure. So the two that I specified. And on the first page of the spreadsheet shows you the possible values you can put. You can put TP, TV, TS, pH, or PS, and they have to be given in that order. You can't put PT. And then given those two properties, what properties can you ask for? And so here's a little demonstration of if I had, say 700 degrees and the specific volume was 0.05, then I get the entropy, pressure, internal energy, and enthalpy. And this is what I'm typing in those cells. So when I click on this cell for entropy, see up here at the top, what I typed was water, parentheses, TV in quotes, then S, the property I want, and then the location of where that temperature and specific volume are. And the units that you must use are shown here. So this gives you some direction. Also, if I want saturation properties, the syntax is a little different. I only give one value, either temperature or pressure. That would be the saturation temperature or the saturation pressure. And then I can get either VF or VG or any of the other listed properties here. And then this again shows the syntax for what you type in that cell. So I've got my first value here, but at this point we probably want to design something. So let's come up with a design. Let me move over to the marker board. Okay, so I know I'm going to have at least one turbine. I'm going to just throw in a reheat, put in a feed water heater, and another turbine, go to a condenser, come out to a pump, then come back into my feed water heater and make this an open feed water heater. Run it into another pump to get it up to the high pressure, and then into my steam generator. Finally back to turbine 1. Okay, so my rationale is that reheat should improve the efficiency. I believe that an open feed water heater will also, any feed water heater should improve the efficiency because I'm doing some of my heating at a lower temperature difference. And so I want a fairly simple power plant to compare to some of the more complex ones, but I want at least my simple one to have reheat and feed water heater in it. So this is about as simple as I can get. And I want to do this with 2 pumps because I think it might be a little more efficient than using a steam trap. Alright, so I'm going to then document that, drawn it out. I'm going to do a quick sketch of what I think the TS diagram should look like so that when I create it on the program, I know what it's supposed to be doing. So I've got state 1, 2, 3, 4, 5, 6, 7, and 8. And it looks like I have a pressure at state 1, another pressure at state 2, same pressure at state 3, and then another pressure at state 4. That stays until I get to state 6, but at state 6, 7, 2, 6, and 7, they're all at pressure 2, and then at pressure 8 is the same as pressure 1. So it looks like I have 3 pressures. So I'm going to draw 3 pressure lines on my TS diagram. Extend these down a little bit. And I know I'm going to start here at state 1. It's going to be isentropic, or maybe have an isentropic efficiency. Going to state 2, then going to reheat it to state 3. Maybe I'll put that up there, come down here, might come out superheated, maybe saturated liquid vapor mixture to state 4. Goes in my condenser, comes out at state 5. The first pump brings it up to state 6. It's a subcooled or compressed liquid. Then state 2, some of it comes off to mix in the open feed water heater, and the fraction that's going to mix here is going to give me state 7. It's going to go into the pump, bring me up to state 8, and then finally go back to state 1. So there's the TS diagram that I'm expecting. And then some fraction of flow that I'm pulling off here, y prime, I can do a quick energy balance there. I know that I want the quality here to be 0. I can find this enthalpy at state 6 from the enthalpy at state 5 plus V delta P, and then I can easily find the enthalpy at state 2, and so I will get that, let's do y prime h2 plus 1 minus y prime h6 equals h7. And that's, there's nothing multiplying h7 except a 1. It's 100% of the flow again at h7. And then finally I can solve for y prime. Y prime is going to equal h7 minus h6, and that's going to be this term. I'm going to bring the 1 times h6 to this side of the equation, so it'll be minus h6, and then I've got 2 terms with y prime. I'll factor out the y prime, and I'm left with, when I divide both sides for that term, it's going to be h2 minus h6. So there's my equation for y prime, and then I, of course, will put that into my model. All right, let's go back to the computer. And I guess for starters, maybe I could take this, or I could make maybe a better model, but take this and put it on my spreadsheet so I have record of that. But I think I might clean that up a little bit and do it in maybe another program where I can get more straighter lines. But for now, I have this reference here. So I've got state 2, state 3, 4, 5, 6, 7, 8, and 9. Now, I didn't put a state 2s and 2 and 4s and 4. I could do that. I'm going to make this simpler and just say that I want a power plant. I'm going to analyze a power plant with an isotropic efficiency of 100%, and then these lines will be vertical, and 100% isotropic efficiency for my pump as well. So you don't have to include an isotropic efficiency less than 1 if you don't want to. It's simpler to do it without it. If you want to look at the example, you can see how I did it, and you can add that to your power plant design if you want. Okay, so state 2, how would I find that? Well, normally I would need to have two independent intensive properties. Of course, one of those will need to be the pressure. And the other one typically would be that the entropy is the same. So it's going to come out at the same entropy. If it wasn't an isentropic turbine, then I would do that first, call this state 2s, and then find the actual state 2. But I'm just going to call this state 2 since it's got 100% isentropic efficiency. But instead of putting this in as a given, or a value that I can change, I'm going to put this in as a formula. And whatever value I got here for S1, I'm going to put that there. Of course, I need to select, let's say, some value. We'll do 5,000 kPa. And this will be, I can copy the units there if I want. Give myself a little more room. Okay, so now I have state 2, and then of course I want H. I'm going to type equal water. The two properties I have are P and S, and they need to be given in that order. The thing I want is H, and I have to tell it where the pressure is and where the entropy is. And I find the entropy. I'll go ahead and copy my units here. And then if I wanted something else, like I do want the entropy, but since it's isentropic, I know I'll just duplicate it here. But the entropy, I don't really have to do this, but is going to equal what was specified. So, and that's just a reference. When I'm doing state 3, I know what entropy is at the exit there. So again, now what do I know at, actually I won't need that because I'm superheating it, so let me just delete that. If it was not being superheated, I'd kind of want to keep that running along. At this point, I know that the pressure, get my mouse to function here, pressure is going to be one of my variables, but that's already fixed, so it's going to be the same as this pressure. And the other thing that I will know is the temperature. This I will change, so I'm going to put some value in. At this point, not really sure what temperature to use. What probably is a good idea, of course, I want it to heat, I don't want it to cool, so I should probably look for the temperature of this state. And so I'll put water. I know pressure and entropy, and the property I want is temperature, and the pressure is here, the entropy is here, and I get 386. So I could either just specify the temperature and note that this is the value, the minimum value that I'd want, which is probably okay, or I could put a DT, like how much do I add to the temperature. That way, if this temperature changes, I'm adding a certain amount. Could do it different ways. If you make it DT, though, then when you put the values in, you'll have to adjust what you're reading for temperature. So I'm just going to put in a value and just keep an eye on this, that this value always has to be higher than this, otherwise I won't actually be superheating it, I'll be cooling it. Okay, so, and this is in C, and this is in kPa. All right, now at this point, since I'm keeping track of things, I'm going to go ahead and highlight the things that I can change. So this I can change, this intermediate pressure I can change. Now, since this is referring to that cell, I'm not going to highlight that, and this is something I can change. Of course, I need to note that it needs to always be higher than this. You could put in some kind of alert, so if you put in low, but I'll see it from the diagram that I did something wrong. And then, of course, I want the enthalpy again. And I know that I'll want the entropy also because of That's how I'm going to find the state 4. And so equals water, and I want to specify TP. I believe it's TP. Just as a reference, we'll go back here and TP rather than PT. And comma the value I want is H. The temperature is here. The pressure is here. And then entropy. Again, TP. I want the entropy. And the temperature here. Pressure here. So you specify them in the order that they're listed here. So temperature first, then pressure. So temperature and then pressure. And you can put in some okay, so I'm up to state 3 now. State 4 is going to be very similar to state 2. So I'm just going to copy these things. Of course, I need a different pressure. So this is going to be my low pressure, let's say 10 kPa. And then my entropy I will get from state 3. That's already there as a formula. So it's using this just like last time. This entropy was getting it from there. My enthalpy is getting it from pressure and entropy, just like before. And the temperature, I don't know if I need it, but it's showing me what temperature it's coming out at. I guess unless I need something else, I can delete that or replace that. Okay, state 5, I know that it's at the same pressure because it's a condenser, so equals this pressure. And then the other thing I'm going to know is the quality. The quality is going to be 0. Now, that's something I'm not going to change. This pressure I'm not going to change, so I'm not going to highlight either of those. It's always going to be a saturated liquid, and the exit of the condenser is always going to be the same pressure as the inlet. And there's no units for quality. Then here the property is a little bit different, so I want the enthalpy and equals. Now here's where I'm going to use the saturation property, so I'm just going to specify the pressure, and I want HF, and then I only need to give the pressure. So there's the pressure or the enthalpy, and that should be all I need at that point. State 6, the two things I know is the pressure, and then this may be hard to classify. I guess that it's isentropic, so I don't really have another property. My property is that the entropy is the same, but I don't really use entropy. So however you want to put that, I guess I can put that S6 equals S5. I don't really need to calculate that. I could leave that off. It doesn't matter, but just so I'm reminded. The pressure at state 6 is the same as the pressure at state 2. I can tell that from my diagram over here. So that pressure is fixed. And then the enthalpy, I'm going to use my saturated liquid approximation for this. So it's going to equal HF at the temperature. So I guess there's a couple ways to do that. I can use this enthalpy, and then I'd have to find the temperature at this pressure. I'm going to do this like I did in one of the examples. I'm going to go ahead and change this to that T6 equals, and I'm going to say that it equals this temperature. And I'm going to put the temperature in here. So the temperature at the inlet to my pump will be the saturation temperature. So equals water, and I'm going to give the saturation pressure. And then that thing that I want is the temperature, and the pressure is right here. So 45.809. Actually, I already had that from state 4. If apparently it's coming out, since I knew the pressure and the entropy, the way I have it set right now, it's actually coming out as a saturated liquid vapor mixture. This temperature might vary from this one if it comes out of my turbine 2 superheated. So, but for now, those are separate equations. All right, so then now this is going to read that, and then my more general compressed liquid equation is, first I need the HF. So I'm going to use HF at the temperature, so I'm going to specify the temperature, and I want saturated liquid enthalpy at that temperature, and temperature is here. Okay, so that's just HF. I'm going to write out my equation here. It's going to be HF at temperature plus VF at the specified temperature times pressure minus Psat at the temperature. Right, so that's what I'm trying to build here, and take the equals off. So that's actually I can write that as H6 equals. So that's what I'm trying to build. Right now I just have the first part, which is, this is my HF. So plus, and I'm going to copy this. So this time I want VF, then I'm going to multiply that times my pressure, which I can select here, minus, and then I want the saturation pressure, which is going to be for that temperature. And then for all these cells, it's based on E21, which is my temperature, and parentheses. So this is HF at the temperature plus VF at the temperature times P, the P6, minus Psat at the specified temperature. And so I've got what I have here, and I get 196.828. Now, of course, this pressure right here is the pressure at the inlet to the pump, so we could use that directly, but I like this format better because then I can copy this anywhere where I know the temperature and pressure and get that value. Okay, so move on here. Now I know H6. H7 is easy. I know the pressure and the quality. Quality is 0, and the pressure is the same as P2. And now I can actually copy this, and if I want the temperature again, okay, and then just to double check that I'm reading it right, so this pressure, and I want HF at that pressure, and then my temperature is the saturation temperature at that pressure. And then I can copy really all of this, because I'm doing the same thing for state 8 as I did for state 6. And this time, though, I'm going back up to my high pressure. And so it came out of my feed water heater at 263. So it heated, my feed water heater heated from 196 to 260, almost 264. And then new enthalpy here. And then I continue on to state 9, which is actually, state 9 is back to state 1. So I can probably delete these. And since I've already worked with that, I can delete that. So there I've built my model. I have all the enthalpies that I need. Now the next step would be to calculate the work or power for each turbine and the Q's. I'm going to set up a little table and then I'll come back. Okay, set up some other inputs and outputs that I want here, and made a little separate table for efficiency and power. I like them side by side so that I can create a table with those values easily. So start with choosing mass flow rate. Of course, that's something I can change. My Y prime is also something I can change. I'll put in, actually, that's something that's going to be calculated in this case, because I decided it's going to come out saturated liquid. So I need to put my equation here from over here. So equals H7, which is this, minus H6 divided by H2 minus H6. And I'm getting that from over here, where I took the fraction of mass flow at one of the inlets, the fraction of mass flow at the other inlet equals the fraction of mass flow, which is 100% times the enthalpy there. So Y prime H, this is 1 minus Y prime over here, because that's what was left after I took Y prime off, and that continued all the way around back to the inlet. And so then solving for Y prime gave me that. So this gives me, I have 32% of the flow is diverted in this case. Then the power for turbine 1 is going to be the total mass flow rate. The fraction is 100% for that, and then times delta H, which I use H inlet, H1 minus H2. Then turbine 2 is going to be the total mass flow rate times 1 minus Y prime, which is now defined here, times H inlet, which is 3, H3 minus H4. The pump is going to be, actually I have two pumps, so I'll have to add another pump, but we'll do the first one, is m dot times 1 minus Y prime times H6, do this as a positive value, minus H5. And these I'm all calculating in kilowatts, so I guess if I wanted to do them in megawatts, divided by 1,000, this divided by 1,000, and my pump again divided by 1,000. And then I'll need to pull these down, get another pump in here. So we'll call this pump 1, pump 2. This will be not 1 minus Y prime, it's the total flow. And instead of, this will be H8 minus H7. Just double check that again. So that's going to be m dot times H8 minus H7. Okay. And then Qn1 will be the steam generator. So that's equal to m dot times 100% times H1 minus H8 divided by 1,000. And my reheat is going to be the mass flow rate times 1 minus y prime times H3 minus H2. So now I've got, except divided by 1,000. And this one, I had already divided by 1,000. Okay. So a lot for the steam generator, not much for the reheat, apparently. My reheat didn't go very high, so of course I can raise that up if I change that to say 500 like the original, then picks up more of the energy there. And then my efficiency is going to be all the power terms, 2 turbines minus each pump, divided by all the Qn, which is that plus that. And the power, I guess I could copy from the efficiency, it'll be the numerator. Paste that. Put an equal sign in there. So the 2 turbines minus the 2 pumps, and in megawatts, since these are in megawatts. So there's my efficiency, so 42.97%, 102 megawatts of power. All right, now the final step will be to make a TS diagram. I think I will show that in a third movie, since it's optional. If you want to get a dynamic TS diagram, you can watch that video, but here I'm ready to do some optimization. Maybe I could start optimizing for P2 if I want. So this, make that my first variable that I'm going to optimize, and of course, set up my table where I put values of P2 and then record values of efficiency and power. And of course the first one I would put would be 5,000, but maybe I want to try a little higher and come lower, so maybe 7,000, 5,000, so on. And I have one of those values already. Copy and paste values. Of course I can get the other values quickly. And so on. And get my 8 values. Maybe find similar to the other problem that that there's some peak. And so I'm seeing here that my efficiency seems to be going up, and as I'm lowering the pressure, so possibly I'll get to some value. Let's try a low pressure. I'm going down to 10 kPa, so maybe 500 here. Oops, back to 5,000. 500. And So 42.95. So I've come down. So somewhere between 4,000 and 500 seems to be a peak. So then I would continue to investigate that and just make sure that I have 7 values in there, or 8 actually, and then make a plot of that and save that in my report. So hopefully this helps, and the last tutorial will be how to make the TS diagram similar to what I did here.